Okay, class, we are going to study about 4.6 rates and related rates. And this is also another part that where we are using calculus in real life. So I want you to look at some examples and then think about it. Some of them you'll be surprised and some of them you may know. So just let's look at our example here, which what I try to say is if you actually from the like stop sign and then you driving your car, and then if you think about your speed, it's not going to be always like 40 miles per hour. If you are driving in regular road, you will actually have starting and speed up, and then you're gonna stay in like 40 miles per hour or 60 miles per hour. But when you look at it, your rate of change in this moment, everything will be changes depending on the situation. So this time, and when you look at this, what 1 second, 2 seconds, and 3 seconds, and 4 seconds, they all have a different rate, relatively different for that moment. So this is the case that we are going to find those relative rates. So if you look at the snowball melts in a way that instant at which its radius is 20 centimeters, it's decreasing at 3 centimeters per minute. So let's draw a snowball with radius 20 centimeters. So radius of 20 centimeters about here. So I will just draw about my snowball like this, with a radius of about 20 centimeters. Then when they reach radius of 20 centimeters, the radius is decreasing 3 centimeters per minute. So when the radius is 20 centimeters, then the rate changes is going to be 3 centimeters per minute. Then I have a question. If your snowball is 50 centimeters, if your snowball radius is 50, then at that time also the rate of your snowball melting is going to be 3 centimeters per minute when your radius is 50. Yes or no? Actually, the answer is no. It's gonna be even thinner. Why? Because you have to think about the volume of amount of the snow melts per minute will be the same. So this volume that will melt in 1 minute has to be same as when you have radius as a 50, and the volume that you are going to add, this one will be melt same amount per minute. That means, do you see that if you have 50 centimeters as your radius, the relative rate at the moment of a snowball melting will be definitely less than 3 centimeters. Then how about when you have a 10 centimeter? Then your volume at that time melting has to be same as this volume. So if you think about just a relative thing that volume same as this volume, then do you see that this will be 3 or bigger than 3? So at that moment, the relative rate of decreasing your radius will be bigger than 3 centimeters. So I want you to see that what's going on. Each time your volume is melting same when it's 50 centimeters and 20 centimeters, 10 centimeters. But how about the radius decreasing? That will be different because you see that this volume is same, but the shape of the circle is radius is different. That this one will be relatively smaller, and this is 3 centimeters per minute, and that's even bigger than 3 centimeters per minute. So I want you to understand why we have to study about relative rate and then the rate. So let's look at here. How we're gonna approach this question is we need to see that what is the fact that they gave it to me. So let's read it again. Snowball melts in a way that instant which is radius is 20 centimeter. So they gave me radius is 20 centimeter. Radius is decreasing at 3 centimeters. The radius is decreasing at 3 centimeters. So how are we gonna write this one? If you get confused how you're gonna write, look at the unit. Unit tell you how to write. So this is going to be dr over dt. Do you see that? Because that's radius over time. So I know this information. dr dt is 3 centimeters per minute. Write down all the units. Units will be the biggest hint in this part. Then what rate is the volume of a ball? What rate is the volume of the ball of a snow changing at that instant? What do I try to find? What rate is the volume changing? So how can I write that in calculus? dv dt. That's how I want to find. So they gave me these informations. Then I want to find dv dt when they gave me dr dt and r. Then how can I connect r and v here? Since it's a sphere shape of this snowball, 3 dimensions, the volume of a sphere is 4 over 3 pi r cubed. So equation of a volume of a sphere is 4 over 3 pi r cubed. So Now, we need to see that what am I looking for? Do you see that I'm looking for this, but I have this? What should I do? I can take a derivative, right? So I'm going to take a derivative by respect to what? Look at the input is r, but I need to take a derivative with respect to t. That means, do you see that I need to take implicit derivative? I need to have an implicit derivative. So let me move here. Then implicit derivative of v is equal to 4 over 3 pi r cubed. That means we're just gonna rewrite it in terms of we have to take this. We have to take the derivative with respect to t. Then all we need to do is just indicate that you are taking derivative with respect to t. So this is going to be dv dt because I'm going to take a derivative. So do you remember? If I'm taking derivative by r, then you don't have to write anything, right? But if you're taking derivative of v, that becomes 1, but I took the derivative by t, not r, then I have to write it dv dt as an implicit derivative. Okay, I hope that you understand here. I'm using implicit derivative that I have to write dt. And 4 over 3 pi, that's a constant. Now take a derivative this one, so which is a 3r squared, but did I take a derivative with respect to t? So I have to write it dr dt. Almost there. So look at, now this is a number, this is a number. Do I know the r value? Yeah, they gave me at 20 centimeters. Do I know that at that time what's rate of radius changing? Yes. So I'm done. Just let's plug in carefully. Hopefully we have room to all squeeze. 4 over 3 pi, 3 times. Now r is 20 centimeters, so it's going to be 20 square. And then dr dt is 3. That's it. And then organize. Do you see I can reduce this one together? So all the numbers that I have is 400, 1200, 30, 40, 800 pi. Okay, let me double check. So it's going to be 12, 40, I think that's it. So what is the volume changing if at radius change 30 and 3 centimeters per minute, then dv dt, the volume changes at that time 4800 pi, while with the unit will be cube centimeter per minute. Okay, so you can relatively see how much is changing at that time. Okay, so that's the answer. Now we are going to do one more very similar problems, and if you want to set up a little bit and do so. If not, just look at one more and then you can try your appetizer, your in-class activities. So let's look at appetizer 2. Appetizer 2 is very similar, but I just switched a little bit of the thinking. So air is being pumped into a spherical balloon so that the volume increases at a rate of 100 cube centimeter per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeter? So let's organize. There's a spherical balloon, and then balloon volume is increasing rate of this. So volume increases, then you said that's the rate. dv dt. How do I know? I cheated. Look at dv dt, right? So it's not cheating. It's I call ethical cheating. 100 centimeter cube per second. And then how fast is the radius increasing? What does that mean? We want to find r dt. That's what I'm looking for. So when diameter is 50 centimeters, this time my diameter is 50 centimeters, not radius. So you have to be careful. So there is information given. And the figure is a spherical balloon. And they're blowing over there. Oh, I made one good mistake above. Do you see that since it's decreasing, I suppose to put -3? Yeah, so that means your volume, everything is correct. Everything is correct above, and your volume also decreasing, so I have to put negative sign. So just please do so, and I'm so sorry, because it's decreasing, that's negative, and I always make small mistake like that with negative sign. So unknown is this one. Then how are we gonna connect the spherical volume between R and B? The equation is going to be the volume equation 4 over 3 pi R cube. Okay, so almost there. As you see, R value I can find is 25 centimeters, and rest of them, what should I do? I need to take the derivative and take an implicit derivative by respect to t. So respect to t. So this one, if I take it, I will write the work here for you. If I take a derivative of v, that will be 1. But I took the derivative with respect to t, so I'm going to indicate dv dt is 4 over 3 pi. And then take a derivative, that's a 3r squared. But I took derivative of r, not t, so I have to write it dr dt. Then now I know this value is 100, so 4 over 3 pi. And this 3 can cancel out, right? So I will just simplify here with r value is a 25 square, and then I don't know dr dt. So let me reduce it, and then I want to just keep in my number this way and look at y, because in calculus you guys have to do a lot of school asks actually do it without the calculator. So when you look at this, I'm going to divide this whole thing by 4 pi and 25 and 25. You may confuse like why she does it that way. I saw something. Now do you see that? 4, 25, this one cancel out. So I got the r dt. The r dt is going to be 1 over 25 pi. So the r dt is 1 over 25 pi. And pi is the denominator, and you have to write the unit. Wow, with the unit. Centimeter per second. Okay. Aren't you curious how much that is? I'm curious how much that will be. 25. I feel that's a very small number. Yeah, 0.127. Okay. So do you know how big is 100 cube centimeters? 100 cube centimeters is going to be not even 7 times 7 times 7 centimeters. 555. 5 times 5 is 125 times 5. 625. So between about 6 and 7 centimeters. So think about this one is about this much volume. That's really small, right? 100 cube centimeters. But if you really imagine it, how do I know that? Because if you multiply 10 centimeter by 10 centimeter by 10 centimeter volume, that's already 1,000. But that is only 100. So that means your ratio will be, if you multiply 5 times 5 times 5, that's a 625. So it's going to be 100, it's going to be even smaller, right? Whoa, how small has to be? 4 times 4 times 4. No, 25. That's 125. Okay, right? 125. So it's about 5 centimeter by 5 centimeter by 5 centimeter. This much is going to be increasing per second. So that's if you think about you blowing the balloon, that's one blow amount. So like about this much. Then how much is as radius? Your radius is 0.1 centimeter. This much increasing per second. Yeah. So I want you to see that in reality, this is the amount you blowing in, because that's about that much per second. And then that 1 second, how much increase? 0.12 centimeter of your radius. And the reason I'm explaining to you, I want you to have a sense of number. 100 cube centimeters is this much. Yeah. We saw that 1,000 cube centimeter was 1 liter, right? So this is basically half cup. 1 cup is 200 milliliters, and that's a half cup. Okay. So here is in-class activities, and then I want you to try it. I know in number-wise it's easy, but I want you to actually understand the concept with amount of the volume as also centimeters. Okay. Okay, class. So third time magic happen, right? Usually if you do 2 or 1 together, and if you do it, you will get it. It's a game. So here, and then if you got the answer, good job, and that's what I got. Yeah, but sometimes you try to think about as also amount-wise. When you see 800 pi cube centimeters, how much would that be? right? So just keep thinking about that. And when you are in reality, you have to have really a sense of all those amount, like 100 cube centimeters was only this amount. So this will be actually how much bigger than this? 24 times bigger because pi is 3.14, right? So just think about that way. 24 times, so about this much is increasing as a volume. Okay, so we're gonna move on to main dish. Okay, so let's look at our main dish. Our main dish is really main dish. This is gonna be pretty fun part. So please always listen explanation carefully. As I said, calculus is not about solving equations, it's about understanding. So here has a 3-meter ladder stands against the height wall. And so I'm going to have a ladder standing in the wall. And then foot of the ladder moves the outward. So here's a ladder, and then the foot of the ladder is moved outward. So here's a ladder here. And what they're gonna do is they're gonna move that one to outward. So we wanna move that ladder to outward, and when this one was 1 meter from the wall, how fast of the top of the ladder falling? So let's see what's going on. Ladder standing, and why we have to do this question. I want to see this part. So you see that I have a ladder, and then I marked it by inches here, and I'm going to bring this one to 1 inch down. And what do you think? Bottom, if I bring this one 1 inch down, do you think then this will also move 1 inch? That's what we think, right? That's why we have to do this. So I'm moving inch down. Do you see that in the bottom? Does it look like inch to you? No, it's not, right? I'm going to move more. Then what's gonna happen? Like this. So every time when you do it, the amount that I'm going down, same amount, inch down each time. But does that mean your bottom ladder also outward each 1 inch? No, it's not. That's why we have to find relative rate. So although I'm putting unit fixed amount down here, depending on where it is located, amount of the ladder shifting to the right side will be varies. So that's what we try to find here. Was it something helpful for you describing this one? So if we do it in the classroom, I do with yardstick, and you will see that this one is a lot bigger than actually what I can show with this little figure. But if you understand that when you're pushing down same amount, it's not gonna be same amount going out. If you learned that today, that's good. If you didn't know, good. If you already knew it, awesome. So now I can explain. The ladder is 3 meters. So let me mark as a red color. So that is 3 meters. And moves outward. So let's put the information. Ladder moves outward. Then I can set this one as X, this one is Y. So I know that dx dt is going to be 0.1. Why did I do that? Well, here says, already gave me hint. It's going to be x over time. So meter per second. Then when the foot is 1 meter from the wall, so they already gave me x is 1 meter from the wall. Already that's 1 meter away. How fast is the top of the ladder falling? I want to see that how this one will be falling. So it's not going to be uniform. It's going to be different. How fast is it falling? What are we looking for? That's dy dt. So let's organize. How much is it falling dy dt? So known is dx dt is 0.1, and I know that x is 1. Unknown, I want to find dy dt. Then what's the function I have to use? What's the function I can connect these two? As you see, there's a triangle, right? What was this length? They said that's 1. What is this length? That's 3. Then what is this length? That would be root 8, right? 9 minus 1, so root 8. Then from here, I can actually see that function I will use will be x squared plus y squared equal to 9. Do you see Pythagorean theorem of this triangle? So that's what I use, x, y, and then the letter size is going to be 3 as a whole time. So that's function I'm going to use. Then what I need to do, let's take a derivative respect to t, because I want to find dy dt. So I'm getting here 2x taking derivative dx dt plus 2y taking derivative. I also take a derivative y, so dy dt need to be written equal to 0. So one by one, let's plug in. All I need to solve for is a dy dt. So let's plug in 2 times this x is 1, the x dt is 0.1, and then plus 2 times, do I know why? Yes, because don't forget it's a Pythagorean theorem. Although they don't give me all information, you have to figure it out by doing it. So that's going to be 2 root 2, and dy dt is I'm looking for, and equal to 0. So we can just leave it, dy dt, and move everything to other side. So I get negative 2 times 0.1 over divide by 2 square root 2. So I get the answer negative 0.1 over 2 square root 2. Okay. So you can punch in this one into the calculator. If you punch in this one into the calculator, then I get about 0.035 centimeters. So answer I'm having, well, you also have to know that some of the schools not gonna let you use a calculator. If you don't use a calculator, or if they don't want to, then you can actually solve this one by hand. I multiply 10 and 10, so negative 1 over 20 square root of 2. Since you cannot mix decimal and fractions, so I multiply 10, 10 bottom and top. If you punch into calculator, that turn out to be 0.035 centimeters. Okay, so what does this mean? What does this mean? I'm going to show you when the letter was 1 meter away, you are moving 0.1 meters. 0.1 meter is 10 centimeters. So I'm going to shift this one 10 centimeters. That's 10 centimeters. If I move as a rate 10 centimeters per second, this much, then how much your letter is going to come down? It's going to be 0.35, that's 3.5 centimeters. So from here, 3.5 centimeters, about this much. If I'm pulling out at 1 meter about 0.1 to the outward, then you are going to, the letter coming down about 3.5 centimeters, which is 0.035 centimeters coming down, okay, meters coming down. So isn't it pretty cool, right? Now, so I calculated when it was 1 meter. Now your turn, I want you to do exactly the same thing, but when it's 2 meters, what's gonna happen? I want you to do the work together. The work that you are going to use is very similar to this one, but definitely your x and y will be changed. X and y will be changed. So let's compare the answer after that. Okay, so let's look at my work. So at the time when it's 2 meters with same condition, is moves outward 0.1, and I want to find dy dt. My equation will be the same. Your implicit derivative is the same. So all I need to do is just finding values carefully. So one thing that you have to see is now your base is 2, hypotenuse is 3. So that will give me my height as 9 minus 4 square root of 5. So only thing that you have to switch is this is going to be square root of 5, and this is going to be 2, and then plug in rest of them exactly same way. And watch that. Those students who doesn't use a calculator, you have to leave the answer this way. We don't use a fraction decimal together, and then punch into calculator shows me 0.089 centimeters. So earlier we had about negative 0.035 something, right? And then now this time when you're doing this 2 meters, you see that how much is sliding is a lot more than before, even twice more than before. It's pretty crazy, pretty interesting, right? Something different than what we actually thought that it wouldn't happen. So that's why math is very important, and now you can prove it. You can show to people, and good job. So there's another one that fresh in you, but kind of using similar idea. So I want you to play it and then compare with me and make it yours. Okay, class, so how did it go your in-class activities? My answer, I got 78 miles per hour, and it's exactly the same situation. I want you to find these values, and the equation that I'm going to use is going to be a Pythagorean theorem. So I took the derivative, and I plug in this one carefully. And as I mentioned before, try to do it without calculator. A lot of numbers turn out nicely, because there are a lot of schools in engineering program has to take calculus without the calculator. So from here, and then I calculated, and then I got 78. That means these cars are coming, and then speed of 60 miles per hour. This is going to be 50 miles per hour. Then how the speed of this one look like getting closer? That's going to be 78 miles per hour. But sometimes you can actually put this one as a negative 78 miles per hour, because you can think as this time my speed is going to be negative 60, negative 50. You could use that. Why? Because I'm coming towards to the intersection. I'm not going away to the away from it, so my distance is getting smaller, so you could use actually negative. But for me, it doesn't matter, because this one, either one, when you use it, the concept is the same for me. So I want you to think about this one, and then that's my answer. That's my answer. And class, with my experience of teaching 4.3, 4.6 optimization and related rate, a lot of my students having hard time in here, because you try to focusing on math part, but I want you to also understanding what's going on, draw the figure, understand the concept of why the rates are different, and then listen my explanation carefully, because it took me also little time to understand fully comprehending it. So probably 3-4 questions not gonna be enough for you to see. Just keep playing, and then keep thinking, and keep think about together with me. It's definitely not gonna be easy doing by yourself, but don't you feel that it's easy when you do together with me, right? Because I know my game. But I want you to also build that skill too, because I'm setting up, break it down for you. That's why when you do my question, oh, she does an easy question, but actually it's not. Like for me, I have my structure built in, but think about why you're doing calculus. Do you see that how much thinking you guys are doing? That's like a 13 to 15 step thinking. That's why you guys are developed. Now you can think really, really deeply and abstract thinking, and that's how I'm training you. So keep doing that, and you guys are doing really, really good. Keep thinking. So this dessert is another delicious one, and since this one is a dessert, I think we're using, looks like the cone shape of the pancake barrel, right? That you're gonna squeeze. The water is draining out the conical tank in such a way that the height of the water is decreased by 3 inches per minute. Units are very important, right? That gives me if it's the original or derivative function. Find the general formula for the rate at which water is draining out of the cone, and usually result to help to find the rate at which water is draining from the cone when the height of the water is 2 feet. Oh my god, how you guys are understanding. So what do you guys remember that we had a shape of the base? I will just make it exaggerate. So if my base shape looks like that, then if you see that relatively how much water is gonna be drained, this volume has to be same as that volume, has same as this volume each, right? So depending on your height, the amount of water draining is the same, but depending on height, the radius can be here, 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 and that rate can be different, right? So that's what I try to find in here, how relatively related each other. So go back, and then now I'm going to organize my thoughts, because I have a little idea. The water is draining out the conical tank. Then height of the water is decreased by 3 inches. So 3 inches per minute. So I see that dHdt is 3 inches, which is 0.25 feet per minute. Why I'm changing to feet? Because I see that my radius or height is using as a feet. So I cannot mix up the unit here. Find the general formula for rate at which water is draining out of the cone. Whoa, cubic feet per minute. So we have to find the volume here. What will be the volume of the cone? Do you guys know that? What is the volume of a cylinder, which is going to be base? The volume of this cylinder is pi r square and h, right? So in this case, I see that my radius is going to be 7 feet, and that's a 12 feet, and I can rewrite this one as a cone. If it's a cone, it becomes 1/3 amount of this cylinder, 1/3 amount of the cylinder. So the equation of that you are going to use is going to be this function. Then we need to see what else I need to find. So your result help you to find the rate at which water is draining from the cone when the height of the water is 2 feet. So height of the water is 2 feet. So they said find the rate of water is draining. Rate of water is draining. What would that be? Rate of water is draining. How can I write in terms of the language here using R, H, and V? Do you feel that that's D, V, D, T? Water draining out, the volume draining out. Okay, so let's organize. Known dH dt is probably, you can use a 0.4, 1/4 feet per minute. And then H is going to be, do I know the H? No, H didn't show me. And then 2 feet. H is when H is 2 feet. So we have to put that one later. And then what am I looking for? D, V, D, T. D, V, D, T. Then how can I rewrite this function? Do you see I have to connect V and R or V and H? I have to connect V and H. So when I look at the function I'm going to use, V is equal to 1/3 pi R square H. Which variable do you think that we need to get rid of it? R or H? We have to get rid of the R because we want to make connection V and H. I cannot have two of those one, and as you see, they don't give me any information about R. They only gave me the information about H. So how can I get rid of that R? There's one part of the equation you didn't notice because they gave me the shape of this one, the relationship between the triangle here. So if you see there is a triangle, relationship between R and H has 7/12 relationship. Okay, one more time. R over H, the relationship is going to be proportional to 7/12. Did you find that? So that will give me equation for R. So from here, what is going to be R? R is going to be just multiply H here, 7/12 H. So far so good? So what am I gonna do? Substitute this one into the R. Then this is gonna give me all the equation in terms of H and V. So 1/3 pi R squared is going to be 7/12 H squared. And don't forget I have H here again. So let's organize. If I organize this one, denominator is going to be 7 and denominator 36. Pi goes to top and H cubed. So that's my new equation for this shape of the cone. Then let's take a derivative so that I can find dv dt. So dv dt is a 7/36 pi times 3h squared. Oh, don't forget dh dt. I almost forgot, right? So let's plug in. Now I will get the answer by plugging everything. 7 pi 36 times 3 times h is 2 feet, so that's going to be 4, right? And then dh dt, did they give me dh dt? That's going to be 1/4, 1/4. And did I plug in everything? Are you guys are following okay? So I plugged in here 7 pi with 36, and now we are going to reduce. As you see, 4 reduces this 4. This 3 reduces as a 12. So I'm almost there. It's going to be 7 pi over 12. That's what I got. So let's look at that amount. I want to see how much would that be. 7 pi over 12. Then I get 1.83. And the unit will be feet cube per minute. Okay, so that's how I found my answer. So how much volume changes when the height as a 2 feet? Okay, and that's the answer. So I want you to keep thinking about it. Okay, class, so did you get the answer? Will you feel a little weird? I got 9 pi over 5 feet cube per second. Okay, if you got the same one, I'm happy, but I'm pretty sure you only understand the math part, so let me help you what is going on here. So why this one showing this way compared to earlier one is more changing it? Because think about this way. This one is a cylinder. Whatever I'm dropping 0.2 feet per second, do you see that the amount decreasing is uniform? Which means every 0.2 second, the volume that decreases will be the same because the shape is cylinder. It's not changing as your volume is not changing like your volume is the same, but it's not changing your radius or height relatively. So in this case, every time you're going 0.2 feet, each time your volume is going to change the exact amount over here, 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 because the shape is like just a cylinder, okay? It's not like this way where it's not shape is changing this way each time. That's why I'm going to show you this one without using calculator, because basically they are saying what is the volume with this cylinder when the height is 0.2, right? Because they are going to reduce 0.2 feet each second. Then I need to just find the volume of the height as 0.2. So look at what is the radius is 3, and then I want to find the volume. That's going to be pi r square h. If I plug in pi, r is going to be 9, and then do you see that h is 0.2, which is 1 over 5. So it is 9 pi over 5 is when you have a height as 0.2, because that's each second, that's the amount of volume is going to be deduced each second. That's why when you look at this one, also you got the 9 pi over 5. I want you to see that what the meaning is and clicked in here. So Younga, why did you plug in your function here already 3? Because my radius doesn't change. My radius is going to be whole time 3. If it's 3 feet, here's 3 feet. This one, if it's 3 feet, that's not going to be 3 feet. That's why I have to leave it. But this case, everywhere is the same as 3. So I just make it inside as a 9 pi, and h is the one that changes, so that I can take a derivative between h of the variables of h and b respect to t. Okay, so hopefully the explanation helped you, and this is it.